Hi, I'm Dr. Incognito. In this video, we'll explore the area of a region determined by a polar curve. We'll consider the curve r equals 4 sine theta, which is a circle centered at 0, 2 with radius 2. And let's consider the region that's swept out as theta moves from 0 to pi over 4, where it just so happens the tangent line is vertical. So this section of the curve, this region, so theta goes between 0 and pi over 4, and r is equal to 4 sine theta. In fact, we can think of this region as being the region bounded by the curves. Theta equals 0, theta equals pi over 4, those would be lines, and r equals 4 sine theta, that would be the circle. R equals 0 would be the positive x-axis. Actually, technically, the whole x-axis, if you wanted to include r negatively. But this is the region we're interested in. So the formula for the area of the region, it would be the integral from alpha to beta of 1/2 f of theta squared d theta, where theta goes between alpha and beta. In this particular problem, alpha would be 0 and beta would be pi over 4. And f of theta, r is equal to f of theta, that would be 4 sine theta. But before continuing with this particular example, I would like to investigate this formula just a little bit. This is equal to the integral from alpha to beta of 1/2 r squared d theta. This formula comes from the area of a sector of a circle. So if that's an angle, call it theta, and this is r. So we have a sector of a circle. Then the area of this sector would be given by, it's a part of a circle. It's a part of a circle. The area of the whole circle would be pi r squared. This is a part of the circle. It is theta 2/5 of the circle. So the area of the sector will be theta over 2 pi times pi r squared, which simplifies to 1/2. I'll put pi r squared theta. I'll put the theta at the back, and I'll cross out that pi. The pi's cancel, notice, so there's no pi in the final formula. The area of a sector is 1/2 r squared theta. And if we look at this integration formula, we see we are adding 1/2 r squared and then d theta, which is a small, tiny little angle, basically an infinitesimally small angle. So we're thinking of our region here as being composed of tiny little circular wedges of circular arc d theta. So add 1/2 r squared and then an angle. 1/2 r squared and then an angle. Okay, so back to our computation then. Our area will equal the integral from 0 to pi over 4, alpha to beta. Recall our theta went from 0 to pi over 4. And then we have 1/2 f of theta squared. That's going to be 4 sine theta squared d theta. When we square this, we're going to get a 16, and then times 1/2 is 8, and then sine squared theta. So we have to integrate sine squared theta. So this is a nice integral. To integrate sine squared theta, we have to use the trig identity. Sine squared theta is equal to 1 minus cosine 2 theta over 2. So substitute that in, and then we will have an integral of the first power of the trig function, which is no problem. So this is going to become 8 times the integral from 0 to pi over 4 of 1 minus cosine of 2 theta over 2 d theta. We can take the 2 in the denominator out, it will cancel with the 8, making 4 times the integral from 0 to pi over 4 of 1 minus cosine 2 theta d theta. And this is now a fairly easy integral. The integral of 1 d theta is theta we have our 4 still. Theta minus the integral of the cosine of 2 theta is going to be 1/2 times the sine of 2 theta. And we have to plug in our endpoints 0 and pi over 4. So this is going to equal 4 times, when we plug in pi over 4, we get pi over 4 minus 1/2 times the sine of pi over 2. And then minus 4 times plug in 0, and we get 0 minus 1/2 times the sine of 0. The sine of 0 is 0, so this one is going to completely disappear. 0 minus 0 times 4. So the answer is 4 times pi over 4 minus the sine of pi over 2 is 1, so this is 1/2. So we're getting pi minus 2, 4 times 1/2. So pi minus 2, there's an interesting number, approximately 1.14. So pi minus 2 is the area of this shaded region. Okay, so there's an example of finding an area relating to a polar curve. Okay, thank you very much for watching. I hope you found this video helpful.